Okay, chapter 4 and section 4.1, extreme values of a function. So here I have a graph of a function y equals f of x. And disclaimer, I just, being extremely lazy, and just blopped out a graph, and this is a horrible graph. It's a horrible graph because it has no tick marks along my x and y axes, so I don't really know how anything is being measured. You should never, ever, ever give me a graph without tick marks. A graph without tick marks is absolutely meaningless. And so you should never do this for me, but of course I've done it for you. I've even printed it, and now I'm putting on a video out there for the whole world to see. But never, ever, ever give me a graph without tick marks. It's meaningless and will be graded accordingly. Now that I've said never do what I've done, what we want to talk about here is what I'm going to call some visual definitions. There are precise mathematical definitions of these things, and if you're interested in the precise mathematical definitions, they are in your textbook, or you can come contact me somehow. Doing these lectures during the pandemic, so I'm not sure exactly how we will be relating to each other, but if you're interested in the precise definitions, contact me. If you're one of my students, if you're just finding weird videos on YouTube, please do not contact me. But if you're one of my students, contact me and tell me you want to know the precise mathematical definitions. These are not precise mathematical definitions. They are what I call visual definitions. An absolute maximum is the y-coordinate of the highest point on the graph. So in this case, we would say that the absolute maximum on this problem would be 7, the y-coordinate of the highest point. The absolute minimum is the y-coordinate of the lowest point. So my absolute min here would be -6. So up here, absolute max. I don't really know why I picked up my red pen to do that. Doesn't matter. Down here, absolute minimum. Local maximum is the y-coordinate of the high points. So local max is -7, -1, and then depending on who you're talking to, 12. The reasons why I'm saying depending on who you're talking to, some people are going to exclude that endpoint because some people want a local maximum to come up and then go back down. Come up, go back down. Come up, not back down. So it really depends on who you're talking to, whether we should include that 12 in the local maximums. I don't care. If you include the 12, that's fine. If you don't include the 12, that's fine. I'm not that picky on it. And it really does depend on who you're talking to. I believe MyLab Math goes with the 12 being a local max. It kind of depends on who you're talking to, how precise they want things to be. So all of these were local maxes. Well, let's just pick a different color. So local max, local max, local max. A local min is the y-coordinate of a low point. So my local mins would be -10. Again, the endpoint, depending on who you're talking to. Some people aren't going to take that -10. -3 and 8. How about yellow? Local min, local min, local min. And then all of those values could be known as extreme values or extrema. Now again, what I really care on this first page is we get the idea that the absolute max is coming from the highest point, the absolute min is coming from the lowest point, local maxes, just high points in general, but not necessarily Mount Everest, and local mins, low points, but not the lowest point on the Earth. And then all these things could be called relative or local, or excuse me, could all be called extrema. And then that, what my little blurb of speech there. You will come out of my word interchangeably local and relative. That just also depends on who you're talking to. 50% of the textbooks out there say local, 50% of textbooks say relative. It's all the same thing. So there's our first part, just visual definitions. Now what we are working towards in this chapter is finding these things giving the rule for a function. Yeah, if you got a graph, yeah, you can point to them. Now you can't point to them with absolute accuracy, but you can get them visually. What we are going for is finding these absolutely precisely given a function. Okay, so we got the same graph again. When I guess I actually already did this. I should have read ahead. Give the extreme values, but we'll go through it again. So find the extreme values. So we already did that. Our absolute max was 7. My local maxes, and we're going to not use endpoints here. And like I said, I don't care that much about endpoints, but what we're going for here, the endpoints are kind of going to get in our way. But if you list the endpoints for local maxes, that's okay. Local max 4, 6. I'm going to have to write these up here. So absolute max, local max, local max, absolute min, -6, local min, -6 and 2. Local min, local min. Okay, so that's not hard. Find the x coordinates where f prime of x equals 0, where f prime of x does not exist. So thinking way back. F prime of x equals 0 corresponded to horizontal tangents or slope 0. Slope 0 or horizontal tangents. So I look at my picture up there where I'd have horizontal tangents. Right there. I could draw a horizontal line right there. So x equal -7. Next horizontal tangent, that's corner point, that's a different thing. Right there, x equal -1. There would be a slope of 0. It's not a horizontal tangent, but it'd be a slope of 0. So 3, and then lastly 8. So that's where I had horizontal tangents or slopes of 0. And then f prime of x does not exist. And I'm going to go out, so I maybe try to say I'm out as far as I can go. That was corner points, discontinuities, and vertical tangents. So we can still see that answer right there, -3. So I'm going to take this information back up on the graph. So I'm going to bring this back down so we can see just the graph. And I'm going to mark these up in red. So f prime was 0, was there. F prime of 0 was there. F prime of 0 was there. F prime of 0 was there. And then the does not exist was here. F prime D and E. So what I want to look at here, ignoring the endpoints, and that's why I said, kind of ignore the endpoints for now. Ignoring the endpoints, everything that's labeled in blue, except for the endpoints. So let's just cover that dude up right there. So now, if we cover up that endpoint, everything that's labeled in blue, every local max or local min, is also labeled in red, but not all red is blue. You got this guy right here where the derivative was 0, but it wasn't a local max or a local min. But there certainly seems to be some sort of connection between my local maxes and mins and where my derivative does not exist or where my derivative is 0. And indeed, there is going to be a very, very good connection, but it's not a perfect connection. Not every place that's red, not every place where the derivative was 0 in this case, was also blue. But there does seem to be some sort of connection. And it turns out that these places where the derivative is 0 or the derivative doesn't exist are so important we give them a name, and that's what we see on the next page. Definition. A number c in the domain of a function f of x is a critical number of f of x if f prime of c equals 0 or f prime of c does not exist. So what we just showed here, or what we alluded to here, is that there seems to be a connection between these things that we're now calling critical numbers, that each one of these places were critical numbers or critical points and local extremes, that there seems to be a definite relationship between critical numbers or critical points, you can call them either, and local extremes. So, in other words, critical numbers are numbers in the domain of f of x such that either the derivative will be equal to 0 or will be undefined. Now some facts here. I'm just going to zoom in a little bit. If f of x is continuous on a closed interval, then f of x attains both an absolute maximum and an absolute minimum. That's just a fact. You're just going to accept it. 2, absolute extremes occur at critical numbers or in the case of a closed interval at the endpoints. 3, all local extremes occur at critical numbers, but not all critical numbers yield local extremes. And we saw this in the picture. So the first one says, if we're continuous on a closed interval, you will have an absolute max and absolute min. Absolutely guaranteed it. The next one says, absolute extremes occur at critical numbers, or in the case of the closed interval, endpoints. Each one of these reds are critical numbers. Critical points. CP, critical point. 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 CP equals critical point. And so this says all absolute extremes occur at critical numbers or in the case of a closed interval at an endpoint. Absolute extreme at endpoint, absolute extreme at a critical number. And the last one says all local extremes occur at critical numbers, but not all critical numbers yield local extremes. And that's what we have there. All my local extremes, everything in blue occurred at red, but this red point was not a local max or min. Critical numbers lead to local max or mins, but it's not a perfect one. Local maxes and mins occur at critical numbers, but critical numbers don't have to be a local max or min. And we'll end that video.